Hello again. This is Math 2134 coming to you from the College of the Page. The title of this lecture is Applied Optimization Problems, and I'm reminding you to be an active learner while watching this video. Life is a word problem, and in the previous section we talked about how to find a solution to certain optimization problems in which the objective function is given. In this section, we consider word problems where you are required first to find the function to be optimized, and the following guidelines are useful in solving such problems. Number 1, assign a letter to each variable mentioned in the problem. If appropriate, draw and label a figure. I guess problem 0 is to read the problem several times. Step 0 is to read the problem several times. Then you do this. Then find an expression for the quantity to be optimized. Then, number 3, use the conditions given in the problem to write the quantity to be optimized as a function of one variable only, because we're only studying in this class so far single variable calculus. That will change later, but now it is single variable calculus. Note any restriction to be placed on the domain of f from physical considerations of the problem. Then number 4, we're to optimize the function f over its domain using the methods of the previous section. Okay. Let's do some examples. They're worth 1,000 words. So here in example 1 is about fencing a garden. So a man wishes to have a rectangular shaped garden in his backyard. He has 50 feet of fencing with which to enclose his garden. Describe the dimensions for the largest garden he can have if he uses all the fencing. Well, we said it was a rectangle, so it's going to have a shape like this. We're going to call this side x. That means that this side is x, and this side is y, and that side is y. And so we know that that's a picture. The area of the garden then is going to be, the area of a rectangle is going to be x times y. So the area is x times y, and that's what we want to maximize. Now the perimeter of the garden, the area all the way around, so we go x, y, x, and y again. That's going to be 2x plus 2y has to add up to 50 because that's how much fencing I have. So what we're going to do is we're going to solve this equation for y. And we'll get y is equal to 25 minus x. Then we're going back to our area equation, and everywhere where we see a y, we're going to put 25 minus x, and then we simplify. So a is equal to minus x squared plus 25x. You see we have turned it into a problem with a single variable. And we are looking at for this to be a rectangle, both those, the x can only be between 0 and 25, otherwise we wouldn't have a rectangle. So f is a continuous function, this a is a continuous function on 0, 25, and so we'll take the derivative. So the derivative of this is minus 2x plus 25. I set that equal to 0, and I find that x is 12.5 is our critical number. Next, we evaluate the function at the endpoints and the critical number. So f of 0 is this. The f actually is the area again. If I put 12.5 in there, I get this. If I put 25 in there, I get that. So the maximum value of this is 156.25, and that happens when this x is 12.5, and if you think about x being 12.5, this tells you that y over here is also 12.5. So we found the dimensions. It has to be a square of side 12.5, and the maximum area that we can get is this. A very nice problem. Here's one for you to try, enclosing the largest area. The owner of a ranch has 3,000 yards of fencing with which to enclose a rectangular piece of grazing land along the straight portion of a river. If fencing is not required along the river, you see this is a different thing than what we had in the first problem. What are the dimensions of the largest area he can enclose? What is this area? You know what to do. Let's see how you did. Well, this problem is different than our first problem because we don't have to have this side. So you see the 3,000 yards are going to be x and y, the way I drew my picture. So this is our constraint. So 2x plus y is 3,000. That means that y is 3,000 minus 2x. Now the area again is x times y. So we're going to have x times what we have for y, turning this into a single variable, which simplifies this way. Then a prime is going to be 3,000 minus 4x, and we set that equal to 0. We find that 750 is a critical number. Now, it turns out that there are not minimum values and maximum values on this, so we're using graphical techniques. And so what we're going to do is we're going to check. I'm using the second derivative test. So here's the first derivative. So the second derivative is minus 4. That means that this is a maximum. And when we put 750 into this equation, we will get the area is, let's see, 1,125,000. And the dimensions are 750 by 1,500. And all those units are, these are yards. This is square yards. Here's an example in packaging. By cutting away identical squares from each corner of a rectangular piece of cardboard and folding the resulting flaps, the cardboard may be turned into an open box. Open box meaning there is no top. If the cardboard is 16 inches long and 10 inches wide to begin with, find the dimensions of the box that will yield the maximum value. Okay. So here's what we're doing. We are cutting squares. So here's the rectangle that we started with. It is 10 by 16. But out of each corner, we cut a square of size x out. So that means that this side, after I cut that out and I'm going to fold it up, this side is going to be 10 minus 2x because I'm subtracting off x on both sides. And this side is going to be 16 minus 2x because I'm subtracting x from both sides. And when you fold it, you get a box then that is 16 minus 2x, 10 minus 2x, and the height of the box is x. And we're going to want to multiply we're going to want to explore the volume. Now, if you look at this, you do have constraints on this because 10 minus 2x must be a positive number. And x has to be greater than 0. So x is greater than 0 and less than 5. And here it is going to be greater than 0 and less than 8. So it's between 0 and 5. Those are the only dimensions that are allowed. So let's move on then. So those are the dimensions of the box. So it's x deep. This is one side, that's the other. The volume is the length times width times height. So it is length times width times height. And I can simplify this, multiply it together, and factor out the 4. And I have this is the expression to be evaluated, and this is the quantity to be maximized. So what we're going to do, and I talked about why it is between 0 and 5, it's continuous on 0 to 5, so the absolute maximum will happen at the endpoints or at a critical number. So if we take the derivative of this, we find that this is the derivative, and we're going to set it equal to 0, so I will factor it again. Make sure you can follow these calculations. So when we set this as equal to 0, we find that either x is 29 over 3 or x is equal to, that's 20 over 3 or x is equal to 2. Since 20 over 3 is outside of 0,5, it is no longer considered. We reject that. We're interested only in the critical number 2. So now we're going to evaluate f at the endpoints 0 and 5 and at the critical number, which is 2, and we get 144. Thus, the volume of the box is maximized by taking x equal 2. And the dimensions of the box are x was 2, and then we're looking at these other dimensions, 16 minus 2x and 10 minus 2x we substitute in, and we get 12 times 6 times 2 inches. And the volume of the box is 144 cubic inches. Again, a very nice application. Here's another applied example. So a city's Metropolitan Transit Authority, we have those in Chicago as well, operates a subway line for commuters from certain suburb to downtown metropolitan area. Currently, an average of 6,000 passengers a day take the train, paying a fare of $3 per ride. The board of the MTA, contemplating raising the fare to $3.50 per ride in order to generate larger revenue, engages the services of a consulting firm. The firm's study reveals that for each 50-cent increase in fare, the ridership will be reduced by an average of 1,000 passengers a day. Thus, the consulting firm recommends the MTA stick to the current fare of $3 per ride, which already yields a maximum revenue. Show that the consultants are correct. Okay. And again, we read this several times to make sure that we can understand it. So step one, we're going to let X be the number of passengers per day, and we're going to let P be the fare per ride, and R be MTA's revenue. You have to think quite a bit to come up with this. But now we need to find a relationship between X and P. Now we observe that the given data tells us that when X is equal to 6,000, P is equal to 3, and when X is equal to 5,000, P is equal to 3.5. Therefore, the slope between these two is given by taking those 2 points, and they lie on a straight line. So, to find the linear relationship between P and S, we're going to use the point slope form of the line, and first we get the slope. So here we use the slope formula, and this is going to be y2 minus y1 over x2 minus x1. We find that the slope is negative, and so now we're using the point 3 and 6,003, I guess. So it is P minus the P coordinate is equal to the slope times the whole of x minus the x coordinate. We simplify this and we get P is equal to this. Therefore, the revenue is going to be how many people rode and the price associated with this. So it's X times P, as we've discussed before. And so when we do that, we get this expression for the revenue. And this is the thing to be maximized. Now, since both P and X must be non-negative, we do have, this is true. And the problem then is to find the absolute maximum of the function f, which is the revenue function, on the closed interval. We've done that before. So we need to evaluate the endpoints and any critical numbers. We're going to take the derivative, and they're taking the derivative of this function. And this is what we get. We set that equal to 0, and we find that x is 6,000. So evaluating the function at 6,000 as well as at the endpoints, we find that the maximum revenue is obtained when 6,000 people ride. Now that means that's what we're doing already, so that means we stick with the $3 as recommended by the consultant. Here's a graph showing you how this is where the absolute maximum happens. And you see it is at 6,000, and the absolute maximum is going to be 18,000. Here's another business example, but this time we're talking about not maximizing but minimizing things. So, Betty Moore Company requires that its corned beef hash containers have a capacity of 54 cubic inches and have the shape of a right circular cylinder and be made of aluminum. Determine the radius and height of the container that requires the least amount of metal. Again, you have to read this several times before you probably understand it. So now we're going to look at the shape of a right circular cylinder. It is shown down here, and you see this is a can. And we're letting h be the height of the can, and we're letting r be the radius of the top and the radius of the bottom. So we have a picture, and we've defined our variables. Now, the amount of aluminum to be used to construct the container is given by the total surface area of the cylinder. So you see we have a surface area of a cylinder here, and the aluminum is the outside. And so what we're going to do is we're going to say, what's the surface area? Well, you have a top of the can and a bottom of the can, and so the top of the can and the bottom of the can are going to be area, pi r squared, because they're circles, and we've got a top and a bottom, so it is 2 pi r squared. So that takes care of the top and the bottom. Now, if I were to unwind this side area, I would see that, oh, I'm going around the circle, which is the circumference of this. I would have a rectangle if I were to cut this and flatten it out. So the one dimension is going to be going all the way around the circle, which is 2 pi r, and the height is h. So this is a rectangle. It is 2 pi r h. So you see the surface area is the top, the bottom, and all around the sides. So this is what I'm trying to minimize. And we do have a single variable here, or at least let me say we want to have a single variable. Right now we have 2. So we have to solve for h in terms of r. But here's what we know, that the volume, which is pi r squared h of a right circular cone, is 54 inches. Because that's what marketing said it had to be. So we can solve that for h, dividing both sides. We have h is equal to 54 over pi r squared. And I'm going to substitute this for h in that equation. And this is what I get to start with. And it can be simplified to this. Again, you should walk through and verify all of these steps as an active learner. So, and we know that the radius, in order to have a can, we have to have the radius be bigger than 0. So now the problem is reduced to finding the absolute minimum of this function on the interval 0 to infinity. So what we're going to do is we're going to take the derivative of this function with respect to r. So s prime is going to be 4 pi r minus, and this is 108 r to the minus 1, so when we take the derivative, it's going to be minus 108 r to the minus 2. And we're going to set that equal to 0. Now when we set that equal to 0, we need to find a common denominator. And the common denominator is going to be r squared. And so we're going to multiply all the way through by that. But then we're just going to look at the numerator, because the numerator is equal to 0 and the denominator is r squared. It's not. So this is the numerator when you get the common denominator. So 4 pi r cubed minus 108 is equal to 0. That means r cubed is equal to 27 over pi. So r is equal to the cube root of 27 over pi, which is approximately 2. And you could find out exactly what this is, at least an approximation of this using a calculator. The exact answer is 3 over the cube root of pi. And so now what we're going to do is we want to find out that this actually is a minimum. So we're going to look at the second derivative. When we look at the second derivative, we end up with, now the second derivative is the second derivative of this function, and the first derivative was this, so we're taking the derivative of this yet again. This is 4 pi r minus, this is 108 r to the minus 2. So when we take the derivative of that, we will have the second derivative is 4 pi plus 216 over r cubed. Now, 216 is positive, r is positive, so this is positive, 4 pi is positive, so this is greater than 0. That means that this is a minimum. So now, what we can do is we can take our expression for h, which we solve for over here. We find out that h is 6 over the cube root of pi. And you see that this number is exactly twice that number. So we conclude that the required container has a radius of approximately 2 inches and a height of approximately 4 inches, or twice the size of the radius. A very practical problem. Here's another problem having to do with minimization, and it's an inventory problem. And inventory is a very important business concept. One problem faced by many companies is that of controlling the inventory of goods carried. Ideally, the manager must ensure that the company has sufficient stock to meet customer demand at all times. At the same time, she must make sure that it is accomplished without overstocking. incurring unnecessary storage costs, and also without having to place orders too frequently, incurring reordering costs. So we have this company is the sole agent for these motorcycles. Management estimates the demand for these motorcycles is 10,000 per year, and they will sell at a uniform rate throughout the year. You could disagree with this assumption, but that's the assumption we're making, and that's the assumption that was made in a very famous paper in 1934 published called the Harvard Business, and the paper dealt with this concept, but it was published in the Harvard Business Review. The cost incurred in order each shipment of the motorcycles is $10,000, and the cost per year of storing each motorcycle is $200. So they face the following problem. Ordering too many motorcycles at one time ties up valuable storage space and increases the storage cost. On the other hand, placing orders too frequently increases the ordering cost. These are conflicting objectives. So how large should each order be, and how often should orders be placed to minimize ordering and storage costs? A very significant problem. But let's deal with it. So we're going to let X be the number of motorcycles that you order each time. And this is called, in business circles, the lot size. And we're going to also assume that each shipment arrives just as the previous shipment has been sold out. That's not a totally real thing, but it's a good assumption. And the average number of motorcycles in storage during the year is X over 2. You see, here's what you're saying. You have a constant demand, so you order X, that means you have X, you sell them at a constant rate, and then you have the new supply arrive right here, you go down again, and you go up and down. So you see the average inventory is in fact X over 2. That's the average. Part of the time you have X, part of the time you have 0, and part of the time you have something that's going down like that. So X over 2 is the average inventory. So now we're going to create the total cost function associated with this inventory. Now, since the company requires 10,000 motorcycles for the year, and since each order is for X motorcycles, the number of orders required in a year is 10,000 over X. Think about this. If each time you were ordering 2,000 motorcycles, then you would say, how many times would you have to order to get 10,000? And what you would say is, well, it's 10,000 divided by 2,000, and that's 5 times. So you see, this is a generalization of that. So this gives an ordering cost of, this was the cost per order, times the number of times you order, and that is going to be 100 million over X dollars for the year. So this is the ordering cost. And the storage cost for those motorcycles is $200 per year, but we take 200 times the average inventory, X over 2, and when we simplify that, we have the cost is equal to 100X. So you see we have the ordering cost and we have the storage cost. And so we want to minimize this cost of the inventory. And the inventory goes from 0 to 10,000, but you see that's not a closed interval, so we're going to be doing this graphically. So to accomplish this, we take the derivative. So the derivative of 100x is 100. The derivative of this is 100 million x to the minus 1. So that derivative is going to be 100 million x to the over x squared, and there's where we put the minus sign. We set that equal to 0, and we obtain that x is equal to, now we're solving a quadratic equation here, so get x is equal to plus or minus 1,000, but we reject the minus because we're ordering motorcycles, not sending them back. And if we were to take the second derivative, that's another derivative of this, the derivative of a constant is 0. This is minus 100 million over x squared, or 100 million x to the minus 2. And when we take the derivative of that, we get this. Now x is positive and this is positive, so we see the second derivative is positive. That means we have found the minimum. So what we do is we're setting this first derivative equal to 0, and we're solving that, and then we said that was 1,000. So we've proven that it's a minimum because the second derivative is greater than 0. So x equal 1,000 gives us the absolute minimum, and so to minimize ordering and storage cost, they should do 10 orders a year, and each for a shipment of 1,000 motorcycles. And here you can see the graph of that function. You see that indeed that is the minimum. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.